This video is about a new type of vertical axis wind turbine that I'm working on. Wow, are you going to continue to watch this? This guy doesn't even know how to pronounce the word turbine.
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 Oh, I guess he's speaking American English. Sorry I interrupted. This video is about a new type of vertical axis wind turbine that I'm working on. And I have a proof of concept made and working, which I'll show to you later in the video. And if everything works out, this should be pretty simple to build so that a home builder could build it and utilize it. So let's dig right in. Wind turbines basically come in two flavors or styles. There's the vertical axis wind turbine and the horizontal axis wind turbine. The large industrial wind turbines are generally of this style. And there's basically one concept of design, and they're fairly well understood by the average person. One of the hard things about it is all the heavy and complex machinery is up in the air, which then requires a strong support. And two of the main considerations for use in a home setting is blade noise and shadow strobe. When the sun gets low in the sky, the shadow of the blades spinning across your windows is very annoying. And whether it's you or your neighbor, this can be a big problem, which sometimes is not thought about too much ahead of time. Another problem is there has to be some system to keep that blade turned facing the wind, and that adds to the complexity. Now, when we talk about vertical axis turbines, there's many different types, and they're basically divided into drag type and lift type. And the lift type has blades, and the drag type may or may not, depending on how it's built. Lift types are generally more complex than the drag type, and they must be started, whereas the drag type is self-starting. Sometimes a drag type is employed within a lift type just to get it started. So, and the lift type also has some blade noise, not as bad as the horizontal axis, because the tips of the blades are not going all that much faster than the wind speed. Here, the tip of the blade can be going up to 10 times the speed of the wind. And these can also have shadow strobe because they're generally individual vertical blades. And a drag type can be built in a way that the shadow doesn't change as it turns. Now, I've included links to a lot more information about both vertical and horizontal axis wind turbines, and videos showing some examples of these, and several videos showing scans, because there are so many different designs of the vertical axis. People don't readily understand them and can't see when something is obviously a scam. So look at the videos about scams so you don't get suckered into that. There's also some scams on low power horizontal axis wind turbines, but generally the situation is not nearly as bad as with the vertical axis. Because the heavy machinery for a generator and so forth can be located at the bottom of the vertical axis wind turbine, a very flimsy support can be used. And in fact, guy wires can be employed. If you make this a bearing so that the vertical support can rotate, it's possible to use guy wires. And because these type of windmills are much lighter than those, the support can really be quite flimsy. Now let's talk about a drag type vertical axis wind turbine, which is also known as a Savonius type. And for the moment, I've simplified things into an arrangement similar to a drag cup anemometer for measuring wind velocity. And here we have two cups on a pivot point, and I have a link below to this article on Wikipedia called Drag Coefficient, where it shows the drag coefficients for various shapes of things that are in an air path. So there's a force equation, it's called the drag equation, where the force on an object is 1/2 of rho, which is the density of the fluid, times the velocity squared, times the coefficient of drag, times the area. It's the cross-sectional area of the thing that's being blown on. So for a cup shape with the wind blowing behind it like this, the drag coefficient is 1.42, and when the wind's blowing on the other side, the drag coefficient is 0.38. So if we have an arrangement here where we're not accelerating, that means that force A is equal to force B. So if we do that, we can see that everything drops out except these terms right here. And for these coefficients right here, we end up with this term equal to 0.517. And if we cross multiply and add and subtract, we end up where the velocity of the cup, it's both ways, is 31.8% the speed of the wind. Now, I think you can see if there was some way to reduce the drag of this cup to 0, that 0.38 would be 0. When you cross multiply, this term goes away, and we end up with VW minus V equals 0. So in that case, the velocity of the cup is equal to the velocity of the wind. Now in either case, to extract any torque out of the shaft, it's going to slow the cups down because it's going to require more force to produce the torque that you're taking away. So, but you're going to have more efficiency when you're starting at almost 3 times the speed. But of course, to achieve that, there has to be a way to reduce that cup drag to 0 in that direction, which you can't totally do, but we can approximate it. And I'll show you how to go about that here shortly. Now, let's think of these cups mounted on a drum, and maybe even have more cups. With that arrangement, it doesn't matter what direction the wind is coming from. It's going to catch in these cups here. And if we could make these cups go away, then we can have that condition there. So I've built a little demonstrator that's a proof of concept to show this in action. So we'll look at that next. Well, I hope you won't laugh at my setup here. But basically, we have a fan to make some wind. And here, this is on a shaft. It's free to rotate. It's basically a coffee can with strips of paper towel. Each paper towel is taped to the can here, and then the ends are taped here and at the bottom. So if the wind were blowing in this direction, it would catch in there. But if the wind's in the opposite direction, it should tend to collapse and therefore reduce the coefficient of drag as the wind blows. So let's turn on the wind here. There, and as you can see, it's self-starting. I put the black background there to help show that over here the profile shows the towels somewhat collapsed, but on this side you can see them bulging out. So the bulging out should increase the drag coefficient over here, and by collapsing on this side, that should reduce the drag. Now that's a rather low setting of the fan. There, I think you can see how flat the profile is over here, and it's quite bulged out over there. So that indicates we're also getting some Coanda effect, where the air is coming around behind the unit. And we're also getting some augmentation where the air is hitting this side. It's then forced to go around the sides. Now, in a real design, I plan to use cloth instead of paper towels and having things attached in a much better way. So that will be our next step, is to enhance this proof of concept a little better. Well, here's our coffee can demonstrator, which we showed will turn in the wind. So let's move up to something a little bigger. How about a nice trash can? So it's a little more realistic. I'm envisioning the next step would be to a large 30-gallon type trash can. And that might be large enough to actually produce a usable amount of power. Now here I've taken a trash can and 2 pizza pans, and the plan is to have our cloth between the 2 discs here. And we can play around with shapes. We can make it like a drag cup anemometer, like our coffee can example. And by proper shaping, we might actually be able to make it into like a parafoil type sail. And we can experiment and see what kind of shape works best. Now, a small diameter thing like this will turn at a higher speed, higher revolutions per minute. But a larger container, although it'll turn slower, it'll produce more torque. And power is torque times revolutions per minute. So there's trade-offs between speed and torque. Now something else we could do is actually go vertically and stack up units basically as high as we want. We could have another pizza pan on top here. So let's try out a set of sails, this time made of fabric, and then we'll go out to the wind tunnel and see what we can learn. Okay, it's time to make our wings or sails or cups, whatever we're going to call these fabric pieces. And if we have a round plate and a cylinder, and then another round plate, we want the sail to be collapsed totally when it's coming around into the wind. So if we draw a cross section of that, we want to anchor our sail here. It has to be long enough when it's collapsed to go around there. And it would be anchored at these points. And the other edge of the sail, we want to be this length, the length between the plates on the end. So that means it's basically a trapezoid shape. So this edge is going from there to there. And this edge is going from here to here. So let's go cut some material. Here I laid out hopefully the blade shapes that I'm going to try and use the first time. That's the trapezoidal shapes. And then I painted the lines that I'm going to cut with a clear acrylic paint. And hopefully that'll keep the edges from fraying. And on a final version, probably you would hem all those lines. It appears gray because I have a piece of gray plastic underneath this cloth. And this cloth is a cotton and polyester mix. Okay, here we are back in our wind tunnel, and I have one of the sails mounted. It's just held in place with black electrical tape. And let's see if it'll turn in the wind. I'll turn the fan on low speed. And here we see it. The sail is collapsed at that point. And there it opens. So as it comes around from the left, it is collapsed and offering minimal wind resistance. And then it opens up and catches the wind. Let's go a little faster. So I'll cut out another sail and add it and see how that works. Okay, I've added a second sail, and we'll turn the fan on low speed again. Well, I might as well add the other 4 sails. It looks like it's going to work pretty good. Okay, here we are with all 6 sails in place. So let's turn the fan on to a low speed. There, I think you can see quite well how they're collapsed as they come around on the left side and then open up when they catch the breeze on the right-hand side. So let's take the speed up a notch. Seems to be working pretty good. Let's go for broke and put the fan on high speed. Okay, I think the next step is to try and get some idea what the velocity of the air is from this fan that I'm using. This device is a pitot tube. It's used for measuring the velocity of air. And right now it's through tubing connected to a differential pressure manometer. The first division here is 0.1 inches of water pressure, and that corresponds to about 14 miles per hour of air velocity. So let's run our fan and see what our air velocity really is. I'll set the fan on high speed. It's hard to show what I'm doing here, but I'm going out to the edge of the airstream and then coming in, and I hope you can see the pressure going up. And we reach just a hair over the 0.1 inches of water. Now as I come into the center of the fan, I'm moving towards the camera. At the center of the fan, I'm showing almost no airflow at all. And then as I continue on across the fan, it's hard to really show what's going on here. But we come back up to our a little over 0.1 inches of water column. So this is a very poor distribution of airflow from a fan like this. Next, let's try and look at the turbulence. I have just a piece of string glued on the end of a stick. And when I'm holding it near the center of the fan, it is rotating. You can tell that there's really a vortex of airflow. As I go away, you can see it's pointing down. And as we come this way, it points up. And again, that's because the air is rotating this way. So we can see how crazy this is. It's actually rotating faster than the camera is showing. So this is a extremely poor setup for testing our wind turbine. But it's all I have right now. Well, we're at the end of this video. I plan to keep on working and come up with the best shape possible and the simplest, easy to build design as possible. And I'll report to you in another video. So if you don't want to miss it, be sure and subscribe so that you'll be notified when my sequel video comes out. In the meantime, if you got anything out of this video, if you click on the thumbs up, that'll help get this video suggested to other viewers. So I hope to see you in the next video.